Okay, welcome back. Today is 16th of February 2022. We are week 6 now on Wednesday. And in this week 6 and week 7, you are all supposed to be doing DTFS and DFT, as well as Lab 3, and to finish tutorial 2A, 2B, and 2C. All right, let us see what are these 2A, 2B, and 2C. So let's go to the tutorial. And in the tutorial, you see 2A is for continuous time Fourier transform. 2B is for discrete time Fourier series and discrete time Fourier transform. And 2C is DFT. Okay, let's see. In 2A, what are you guys supposed to be doing is that you are doing these questions, which is on the x-axis is time and the y-axis is the function. So time is real, so you have a very smooth thing going around. Okay, so you have to do very basic continuous time Fourier series, basically meaning analyzing periodic signal that is continuous in time. What about continuous time Fourier transform? Means you are analyzing an aperiodic signal. So this signal lasted from minus A to A and then doesn't repeat. Okay, of course you can say, do I have a signal that goes from negative infinity to infinity and doesn't repeat? Is it continuous time Fourier transform? Yes, you can. But of course, how are you going to integrate, right, if it is non-zero? So that's another problem. This one is another problem, right? This doesn't go to zero. Can you see? This exponential will never go to zero, but yet you can perform continuous time Fourier transform. So maybe that answers your question. All right. So in this tutorial 2A, it is a revision of what you have done in Math 2. Okay, so it is the first 4 questions is nothing but performing continuous time Fourier series analysis and continuous time Fourier transform analysis on this kind of waveforms. The last one is on property, the property of shifting property and convolution property. The answers have been given to you, so just go through a quick read, and this is assumed knowledge. What about our proper problems to solve, which is 2B and 2C? 2B and 2C's in 2B, I'm going to use this example. So the first interesting thing about this example is that now my horizontal index is discrete time 0. In fact, it's not time, it's just discrete sample index. Sample index 0, 1, 2, 3, 4, 5, 6. The most important thing to remember about this guy is that he is a periodic signal. Okay, so in a periodic signal, then we can do Fourier series. Remember, Fourier series is primarily for a periodic signal. Actually, you can use Fourier transform for periodic signal as well. So that's what we did. But typically, we are doing Fourier series. The first 2 characters is DT, discrete time, because our samples are sampled signal, not a continuous time signal. Okay, so you should do at least question 1 and then get all these things up. So question 2 is again very simple. It's just a different version of question 1. We just change the waveform and you're again asked to find DTFS because this guy is again periodic. Then again, we're asking you to find DTFF of this guy, right? Some cosine wave and another. So again, this is periodic. That's why we are doing DTFS. So question 2 and 3 are a little bit different because here I only give you a equation. Here I sketch for you. Okay, so if you cannot compute cosine pi over 4 for n, then you cannot find the period, then you have no idea how to solve this. So let me explain what did we jump here. Here, the values of 1, 2, and 3 for time index 1, 2, and 3 is obvious. So you have nothing. You just plug in this value and you can compute DTFS. Here also the same. Here you identify, okay, the period is 10 samples. That's the important thing to take home, right? X0 equals to X10. X1 equals to X11. Oh, okay. So big N, the period is 10. What is this individual value from X0 to X1? 1. Okay, we can plug into the equation and we solve. That's DTFS. Here is different. I given you an equation. I never tell you it's period. So to play with DTFS, you have to find the period, you have to get the values and plot it out, and then you have to calculate it. Okay, so that's the idea. All right, so some more. Question 1, 2, 3, DTFS. Question 4 onwards, DTFT. DTFT means what? FT, Fourier transform. DT means discrete time. So I better give you a discrete time sequence. So h of n means, oh, n is time index 1, 2, 3. Therefore, yes, we know that we are playing with discrete time. How do we know that this guy is aperiodic? Okay, you go and plot this. This is half, just now that exactly the same, same, what do you call that? Same hn I was playing with. Half to the power of n, where n equals to 0 is 1, followed by half, followed by half squared, half cube, half whatever. So this is a infinite impulse response. This infinite impulse response can only be analyzed by DTFT. Okay, okay, so that's the idea. How? You go and see the answer in 4A. Right, so DTFT, yeah, I guess you have to play with all this, and then we're done with DTFT. Now, how to study this course? Please look at this slide. Go to lectures, and in O3B, I guess the slide that will teach you the most thing is, I guess, this slide. So you have a one-page cheat sheet. So I guess you have to copy this slide inside somewhere so that all the equations are here. And then you can, when we're asking you to do DTFS, remember DTFS means the signal is discrete time and is periodic. So you can see that this is periodic. Important thing is we have to identify n, big N, the period. This big N will be plugged into here, 1 over n, the big N, and 2 pi over the big N. So this is where the big N is going to be used. The other thing where we're going to use the big N is K. K will be equals to 0 to n minus 1. Same with this. N equals to 0 to n minus 1. So the big N is a very important number. If you cannot find the big N, you can play with this. Okay. All right. So this guy is called the analysis equation. We take the input sequence, xn, and we analyze it and break it into the frequency representation C, K equals to 0 to big N minus 1. Now, you can perform analysis, discrete time Fourier transform analysis on periodic signal as well. The equation is like this. Typically, of course, discrete time Fourier transform is to analyze a periodic signal. When we analyze a periodic signal, it means that the signal goes from n equals to negative infinity to infinity. Because he's aperiodic, he has no period. However, if xn, right, have values from n equals to negative infinity, actually this equation totally don't make sense. Because how are you going to even sum, right? If there are values there, how are you going to sum? So this equation is a bit strange. So in our example, we are actually, most of our kind of exam questions example is that this xn, see, only have two values that is non-zero. The rest of the values are zeros. So this problem reduces to actually summing values of non-zero multiplied by this complex exponential. That's it. Okay, otherwise, then you say, sir, how are we going to use this equation to analyze this guy, right? Because he says, hey, he's aperiodic. He's going to repeat himself. So he's going to exist from negative infinity to infinity, right? How are we going to do this? So there's a special case, and we're going to use impulse to represent xej omega. All right, go to the lecture notes and you see that. So in tutorial 2B, you're going to use this equation mainly. To reconstruct, we're going to use this equation. What does reconstructing means? It means that if I give you all the CKs, you can reconstruct xn. Okay. Now, maybe to really understand this, you have to, oops. you have to do this. You have to, I guess I'm going to start with this example first. Okay, so let's try. Oh, not this one. O3A. Yeah, this is the example. All right. So if you come out of this course and to understand Fourier, maybe this is the only picture you really need to understand. Okay, and then you can what do you call that? You have at least a big picture of Fourier. Now let's try. Fourier means we always start with continuous time. We have an input function that is repeating. So Fourier says if you have an input function that is repeating in continuous time, you can actually represent it in the frequency domain. How? So we call this representation the Fourier analysis. We analyze this and represents this original waveform in the frequency domain. We don't lose any information. We can reconstruct back the original waveform by synthesis. So analysis tells us what's inside this waveform as sum of sinusoids or complex exponential. Analysis takes this guy and reconstruct him. So you can think of this as a recipe. Whatever you see, you write the recipe down, and synthesis means from the recipe you reconstruct. Okay, right. So what does the recipe contains? So I'm going to show you what the recipe contains now. So in the recipe, the x-axis is frequency. There are two information. X-axis is frequency, x-axis is frequency. Analysis tells us at this frequency, there's something there, some 10 value there. At this frequency, there's some 3 value there. At this frequency, there's some 5. This frequency, there's 4. Nothing else in between in this particular analysis, okay? And here, when I tell you the magnitude, I have to tell you the phase. So you should be able to guess what am I telling you that this exists. It is actually telling you at 10 hertz, there is I think I'm just going to guess, a cosine wave or a sine wave that have amplitude 3 with 0 phase. At 20 hertz, there's a sine wave or a cosine wave. Let's try to figure that out later, with a phase shift of pi plus 3. So how to do this from here to here is, of course, your math problem. How to do this from here to here and show that it exists is a very high level math problem, right? That means, does it exist? So it's not our problem to solve. In our level, which is second year or third year undergraduate, all we're interested in is, we say this, we can generate this guy through the Fourier analysis. But the most important understanding is actually to interpret this. What does this tell us? This tells us to reconstruct this original green guy, all we need to do is to take this guy plus this guy plus this guy plus this guy with this phase shift, and we can reconstruct. It tells us what are the frequencies that exist here. That's it. All right, let's see. So that green guy was this waveform. He is a constant. Sometimes we call it DC, a constant plus a cosine. So actually I'm playing with cosine wave. Cosine with amplitude 3 and 10 hertz. Amplitude 5 and 20 hertz with phase shift of pi 3. And 30 hertz is 4, but it's sine. But I can change the sine into cosine, right? At 30 hertz. So let's go and see the 10 first. At 10, DC. What is DC? DC is actually a cosine with 0, what do you call that? 0 frequency. Because cosine of 2 pi 0 is what? Cosine of 0 is 1. So actually, 10 is a cosine with 0 hertz. So let's see. So imagine now this horizontal axis and these values are representing the existence of cosines at different frequency. Cosine at 0 hertz, amplitude 10. Voila, we got the first term. What about the second term? 3 cosine this guy. So I have an amplitude of 3 at cosine 10 hertz, no phase shift. Let's go and see our figure. 3 at 10 hertz with phase shift of 0. Okay, so now I can guess this guy. 5 at 20 hertz with phase shift of plus pi over 3. Let's go and figure it out. 5, 20 hertz, pi over 3. 5, 20 hertz plus pi over 3. Okay, and the last guy is 4, 30 hertz, but sine. 4, 30 hertz. Why minus pi over 2? Because to convert cosine to sine, we must introduce a phase shift of minus pi over 2. Right? So now you can see I go from here to here. It's nothing but decomposing my original signal into cosines with different amplitude, different frequency, different phase. Isn't this a very nice and compact representation of this guy? So that's what Fourier analysis is about. I will now transform, or another word for change, my representation along the horizontal axis in time to a horizontal axis in frequency. So this is a frequency domain representation using cosine. Okay, and later on, of course, after this, you will realize that cosine is not the simplest. It's not the simplest signal. The complex exponential is. So later on, we'll represent the cosine as complex exponential. Okay, I will pause now and take questions. All right, so now we understand that we can perform analysis and we see the input signal into this frequency representation. And then we can reconstruct. So the reconstruction is called synthesis. Okay, so that's the clever idea. All right, so let us see what else we want to examine. There's another way we can see this. So when we analyze this, we know at different frequency, have this information, and then in time, we can actually add them up. Okay, so in fact, that's what we actually did. Once we can see that this is 10 at 0 hertz, we generate a signal, just a continuous variation of amplitude 10. This guy, at 10 hertz, we have amplitude 3. So we have 10 hertz, this is continuous time, and amplitude 3, and with phase shift of 0. So do you see this is a cosine? And so on and so forth. And then when we add all of them up, it's this guy. Wonderful, isn't it? Yeah, so it's very, very cool. Okay, so this is a synthesis. That means from here, we generate each one of them, and we add them. Okay, yeah, there, the synthesis part. All right, what else is there? A spectrogram. So in lab 2, you'll see what a spectrogram is. So this is x-axis is time, y-axis is the amplitude. The bigger it is, the louder it sounds. So this is actually the telephone signal where you press 1, 2, 3, 4, 6. This is maybe, this is something else. So I look at this, I know, I whistle. And this is speech. Maybe I say, hello, how are you? Right, how do I know? So in the spectrogram, what is a spectrogram? So, oops. So maybe I should show you a Fourier transform first. I take a very short part of the signal, where between the two yellow line is, and I perform Fourier analysis. X-axis is frequency, y-axis is the amplitude, the magnitude. Most of the time we ignore the phase, we just see the magnitude. What does this tell us, Benedict, this picture? For this guy. What's the interpretation, Benedict?
It's the signal energy, is it?
Yes, it's a signal energy. And what does this two peak tell us?
Those particular frequencies have the highest energy.
Correct. So in fact, can you shut down your mic first, please? So in this example, at these two frequency, there's two peaks. That means actually he produced only these two frequency. Nothing else in between. Can you see? Nothing else in between. Okay, because actually minus about 40 or 50 decibel is negligible. You can't hear a thing. Huh? So here is a lot of low frequency. There's all this frequency has no signals, and only at these two have high signals. All right, what about this guy? Here, one signal, one signal. Actually, here is I'm blowing like, so here is I'm blowing. What you realize is that even when I blow, I cannot produce a pure sinusoid. So there are multiple frequencies existing in its harmonics. That is a natural of things. And actually, when I speak, right? Wow, there's a lot of frequencies going on. It's a very beautiful shape. This is frequency and this is amplitude. Now, what about a spectrogram? How do I convert from here to here? So all I did was actually, I take a small slice, I generate an analysis, I put it here. The higher it is, the sharper the color. Then I take the next slice, I put it there. So a spectrogram is nothing but a very complicated looking Fourier analysis, stacking it up so that I can now see what's happening along time here and along frequency here. Okay, guys? So in fact, right, in lab 2, I asked you all to analyze a spectrogram, to use a spectrogram. Okay, I'll pause now and take questions. Okay, so we are done, and now we are going to show you why Fourier analysis is complicated for students. It's because there are many of them. So how do we break Fourier analysis? First is you have to look at the signal. X-axis is time and continuous. So we call this a continuous time signal. In this case, he repeats, so we call him a continuous time periodic signal. This guy doesn't repeat, we call him continuous time aperiodic or not periodic. So we have two cases here now. Continuous time periodic, continuous time aperiodic. Now, to perform Fourier analysis, we can either do continuous time Fourier series or continuous time Fourier transform. So don't be fooled, okay? You can use Fourier transform for aperiodic signal as well, although it's not often used. However, if the signal is aperiodic, we can only do Fourier transform, continuous time Fourier transform when the signal is continuous time. So this is the tutorial 2A. Tutorial 2B, all right. We go from continuous time to discrete time by sampling. We sample this guy to this guy, we sample this guy to this guy. In this particular case, I should go up, 0, 0, 0, up. It means that I sample this guy twice and this guy 3 times. So the periodicity is 5 because after 5 samples, it repeats himself. Okay, here the signal is discrete time. He is periodic, so I can use discrete time Fourier series because for periodic signal, I can also use Fourier transform. So I can also use discrete time Fourier transform. The last one is a sampled version of XT, aperiodic signal. I get up, 0, 0, 0 forever, 0, 0 on the left forever. This is aperiodic discrete time. So I can only perform discrete time Fourier transform. So now I have 4. And in fact, you will think to yourself, this is all I have, which is totally true. But because we are engineers, we were going to do something else. And it's called DFT. And in MATLAB, it's called FFT. FFT is a fast version of DFT. Okay? So every time you say, see FFT, it's actually DFT. What is DFT? Okay. In the real world, let's say we have up, 0, 0, 0, which looks like this guy. But outside of here, he's something else, totally different. However, if we pretend that the world we are looking into is only this guy, and we perform DFT, we're actually taking these 5 signals and performing DFT, analyzing these 5 points only. When we do that, actually we are bluffing ourselves to think that outside here and here, it is exactly like this guy. It is repeating. Every time you take Fourier transform, right, or in here, you take Fourier series, you are thinking that he is repeating. Okay, there is a period. And so you have to be very careful when we play with DFT. All right, so we have these 5 analysis equations. Now let's see the equations for. So this is the mind map that you have to copy into your cheat sheet and bring it to the exams, because I'm not going to give you any equations at all. So let's see I'll ignore this because I will assume that this has been done in math too. And now I play with only this guy. Okay. Maybe I would just briefly go through. To perform analysis, the word analysis means to take my original signal and put it into the frequency domain. So you say, where is frequency domain? Here you can see omega, so that is the frequency domain omega. Here you say k, where is frequency domain? So in the past exam questions or the tutorial, you have to find what is the relationship of k to the frequency. Okay, so that's a hint for you. All right, so this analysis breaks the original signal. How do I know that it breaks the original signal? You see, the input to your analysis is xn. Therefore, whatever come out is the frequency representation. That's how you look. See, I send him the xn, out comes the something representation in omega. So these two are the analysis equation. DTFS, DTFT. What about the synthesis equation? Synthesis equation takes the Fourier representation, which is a CK. See, the input is the CK, the output is the XN. So this is a synthesis equation. I take the frequency representation, I pop out the XN. Same, XEJ omega, I push in the XEJ omega, the frequency representation. Now look, why is it integral and why is it sum? Because in integral, omega is continuous. I am playing with xej omega, and xej omega is a continuous function with respect to omega. K, only have k equals 0 to n minus 1. Wow, very few. Huh? So if n is 8, 0 to 7 only. C0 to 6. If n is 1024, C0 to C1023. So that's the difference. One is an integral from 0 to 2 pi, or from minus pi to pi. And the other guy is called k equals 0 to n minus 1. But anyway, the take-home message is this. In synthesis, I take the frequency representation. Here is obvious. My frequency represented in different omega. CK, later on you'll see, it exactly means the same thing. My representation at different k, and k means different frequency. I take this and I sum and I reconstruct. Actually here, this little guy, actually once you understand this, then it reveals the entire Fourier secret. You look at this guy, he says my xn is nothing but a sum of complex exponential at different frequency. That's it. So what is Fourier doing? Fourier breaks my signal xn into sum of complex exponential, telling me different frequency. This is different frequency, right? K times different frequency. CK is reviewing the magnitude and the phase. So in fact, this little equation here, this equation, if you look back at the slide, it is actually doing exactly, yeah, I mean, you can think of it as doing exactly this guy. My xt is the sum of complex exponential. You think later on, I can break my cosine into complex exponential at different frequency with different phase shift. All I need to tell you is the amplitude and the phase at different frequency. You look at this equation very carefully and you can cast it into exactly this form. And that's the secret. Once you understand this, That's it. That's all there is to know. And all that is left for us to do is to make sure that we can find CKs. Okay. Now I will pause for a little while. Now we continue to have this big picture of this figure. Let's look at the last figure, which is the DFT. A DFT is the engineer's Fourier transform. The DFT realization in MATLAB is called FFT, means fast Fourier transform. So if you type FFT something, it's actually implementing DFT. Now, DFT, you notice that in the real world, most of our signal on the left and the right doesn't repeat. So it's not so nice like this. It's not so nice like here, because here it dies for the second part. Most likely our signal is something in the middle is what we're interested in. Left and right, we're not interested in this. So we are only taking this, in this example, 5 samples and analyzing it. And we are very sure that whatever is on the left and on the right is not 0, like above, or not repeating like the other guy. But look, this guy is exactly this guy, and is exactly this guy. So something must be going on. Something must be going on, and they are very, very similar within these 3 guys when we do Fourier analysis. And that's the difficult part to understand. You realize that in my notes, I'm spending a lot of slides telling you that when you analyze these 3 things, they are very, very close to each other. Okay, and then the problem is how to interpret. All right, let us see the the DFT analysis. The DFT analysis takes the input signal, and I call him X3 here. So this is X3. And I'm only examining from n equals to 0 to n minus 1. So I must fix the big N, and big N tells me that I'm only going to look at these n sample points, and I'm going to multiply by complex exponential. So the input is the sequence, and the output is the frequency representation. All right. Now, you'll realize that, hey, this guy looks very much like this guy, except for n equals to minus infinity to infinity. And except for this guy is continuous omega, this guy is not continuous omega. In fact, this guy looks exactly like this guy, except 1 over n. So there is just a scaling between CK and XK. Okay. So this is the first relationship, and then you have to figure out a couple more. Now, since 1 over n exists here, and 1 over n didn't exist here, you can see they just simply move the 1 over n from one side to the other side. So that is why it's very confusing, and you have to write these 6 equations now not to be confused. All right, so DFT can be used to calculate this guy, right? Just this guy, and then you stuck 1 over n in, you get CK. So that's the first trick that you will learn. Yeah, later on, if you want to compare your DTFS to FFT, all you need to do is compute FFT, divide the coefficients by 1 over n. That's it. Okay, so that is between DTFS, DTFT, DFT. Okay, I think with that, we're done. Okay, so now I'm going to draw for you this figure called omega. This small omega here and CK here. So I told you that we are taking the input signal xn and we are converting into a frequency representation CK. Xn, xeg omega. Here, you believe me, because omega goes from 0 to 2 pi or minus pi to pi. Here, you say CK, where is frequency? So I'm going to show you frequency. Here is a input signal, discrete time, that is periodic, dot, 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 repeating himself. CK is this equation here. When I perform DTFS, I will get C0, C1, C2 until Cn minus 1. So in fact, I'm only interested in C0 to Cn minus 1. Why am I not interested in Cn? Because actually Cn and C0 is the same. C1 is the same as Cn plus 1. Wow. Cn minus 1 is the same as C minus 1. So you can figure out now that when I compute C0 to Cn minus 1, that's good enough because I don't need to compute Cn to C2n. I do not need to compute C minus n to C0 because they are periodic. Now, this is K. So how is K related to 2 pi? 0 is related to 0 here. This is radians per sample. 0 to 0. N is 2 pi. Okay, this is how it's meant. All right, where is this shown to us? Actually, it is shown to us here. K times 2 pi over n. Each of this line of K is actually a multiple. The frequency that we are interested in is K times this frequency, 2 pi over capital N. When K equals to 0, 0 times 2 pi over N is a 0 frequency. When K equals to 1, is the 2 pi over N, the fundamental frequency. K equals to 2 is 2 times the fundamental frequency. So where is it? This is K equals to 0, K equals to 1, K equals to 2, K equals to 3. What we did was we basically break 0 to 2 pi into big N parts so that you can only see things at these discrete frequencies. So this is one big deal for Fourier analysis. Fourier told us, right, in his nice little equation, if your signal is periodic, don't bother about all this frequency in between this omega naught. Nothing there. There is nothing there. All you need to reconstruct this guy is to use the 0 frequency, omega naught frequency, which is 2 pi over big N. The second fundamental frequency, which is 2 times 2 pi over N. The third one, and until, in fact, you don't need for all, you only need from 0 to N minus 1 because the rest is repeating. Okay, so there are a lot of things going on here, and only when you read the slides, and I will tell you these things. But for the big picture, you don't care, right? You just plug in this equation and see this figure. So in some of my diagram, I plot 0 to N minus 1. In some diagram, I'm going to plot from minus N over 2 to plus N over 2 to represent from minus pi to pi. Sometimes I prefer to show you from 0 to 2 pi. Sometimes I prefer to show you from minus pi to pi. But now you realize if I show you from minus pi to 0, it is nothing but showing you from pi to 2 pi. No difference. Okay? So the symmetry is always there. All right. So maybe I spend the last 2 minutes talking about this. When the signal is aperiodic, that means this guy goes on forever. I need to perform analysis using discrete time Fourier transform. Here, omega will go from 0 to 2 pi, but continuous. That means I need to substitute every value of omega, 0, 0.0001, 0.0002. But of course, in real life, I don't need that. I only plug in a few, densely populated numbers, and then this curve becomes smooth, and that's it. Okay, that's all there's to it. And in fact, you realize that in the lab, most likely I'm going to ask you to plot 0, omega equals to 0, omega equals to 0.1 pi, 0.2 pi, 0.35, or 0.25 pi, 0.5 pi, so on and so forth. That's it. Okay. So I think I will now